So we're going to start here with a picture where we have some angle theta measured in terms of standard position, where we're saying that's counterclockwise above the x-axis. As I said, I'm not going to be too picky about standard position, but for this, it helps to think in that way in particular. And then we'll say we have some point P along the terminal side of that angle theta. That is, you think of it as being a ray. P is along some point. And sorry if this picture's a little bit blurry, but we're going to make the best of it. It's going to be shrinking back down to a more reasonable size in a second here. But the point is, if we're thinking about that angle, if we're thinking about that point, and we want to talk about how far away that point is from the origin, we would get a value which we're going to call r, because we think of that as being like a diameter through that circle, or more like a radius, really, in this case, where that radius is measured in terms of the x and y coordinates of that point. That is, r is equal to the square root of x squared plus y squared. And as a result, we can think of that relationship there. We can think of that point in terms of a radius, x and y, acting something like a right triangle. And that's how our discussion in terms of trig functions should always be thought of, at least in my opinion. That's where most of the relationships we're most comfortable with come from, and that's where we're going to develop this idea of being able to measure a trig function in terms of any angle. The point of any trig function is to tell us something like a radial measurement in terms of an angle that would generate it, but thinking of that kind of abstractly is a little bit hard to grasp, so we're going to center that a bit more onto the idea of a right triangle to better bring together the concepts as we've seen them so far. But with this construction in mind, we can think of how we would be able to define the 6 trig functions in terms of that angle and that point, that is, in terms of the right triangle that they implicitly form, where we would have that sine at that angle theta is equal to, usually, something like a y value in terms of a unit circle. But because we have a little bit more information here, we have a little bit more room, we're not just talking about the unit circle in terms of that angle anymore. Usually we will, but in this case we're not. We have y over r instead. That is, opposite the height over hypotenuse, which here is r. Meanwhile, for cosine, we would have x over r, because x is the adjacent side in terms of that angle theta, and r is still the hypotenuse. And then finally for tangent, we have y over x, opposite over adjacent. Here is still something like vertical over horizontal, just like when we talked about these things in the earlier sections. Meanwhile, for cosecant, we'll still just have 1 over the relationship for sine. In this case, 1 over sine will take the form r over y, assuming that y is non-zero, while secant is r over x, 1 over cosine, assuming that x is non-zero, and cotangent is x over y, assuming that, again, y is non-zero. And to help see this a little bit cleaner, to help see this a little bit clearer, we're going to take a look now at an example. So for our example, we have the point P equals 1, negative 3 on the terminal side of some angle theta. And we want to find the value of the 6 trigonometric functions at that angle theta. So for this, what we should really do first is give ourselves some sort of picture to understand what it is that we're looking at, to get a better sense of the behavior between this angle and the sort of right triangle that we're going to be trying to manufacture out of the relationships between our point and that angle, where in this case, notice that the angle kind of comes all the way back around. So when we're looking at what happens in terms of a right triangle, we're not really using the whole thing. We're using that tiny bit that gets us back to the x-axis. that hints at a construction called a reference angle that I'll say we don't need to know by heart. It's not the most important definition to really have down in detail, but as long as you get a sense of what it is that we're trying to work with, that's good enough. Anyway, with that picture in mind, let's make sure that we understand we have our x value is 1 and our y value is -3. So if we want to get something like a radial value, something like the hypotenuse of the triangle generated by this point, we would be looking at the square root of 1 squared plus -3 squared. 1 squared is 1, -3 squared is 9, so you get root 10. And I'll say for this, don't worry about simplifying or trying to get a decimal form. You're best off leaving it in that admittedly kind of ugly form. It's the nicest we're going to get, it's the cleanest we're going to get, even though it has a radical in it. So just leave it like that. But from here, we've got an x, we've got a y, so we've got 2 leg lengths, as it were. And now we also have a hypotenuse length, that r value. So if we want to start getting our trig functions, we can start with sine, where for the sine function, as we see here, we want something of form y over r, where y is -3 and r is root 10. So we get -3 over root 10, which you can multiply by a specially written form of 1 to turn into -3 root 10 over 10, if you want to get it a little cleaner. But for my money, I'm okay with 3 over root 10 because it shows a specific understanding of the relationship, and that's really the point here. Meanwhile, for cosine, we would have x over r, so 1 over root 10, which simplifies for essentially the same reason to root 10 over 10 after a little bit of algebra, but 1 over root 10 is fine for me because it tells the story that I need you to be able to show. And then for our other 4 functions, we can either find them essentially in terms of these two, or we can find them using our coordinates, where we would get that tangent y over x is -3 over 1, or -3. Cosecant r over y is -root 10 over 3. You can also think of that as being 1 over sine. Meanwhile, secant, 1 over cosine, is r over x, which here would just be root 10, because root 10 over 1 is root 10. And then finally, we have cotangent, which is x over y, and that comes out to -3 in this case. So in this section, we're going to be looking at this type of relationship. We're going to be trying to define values for our trig functions that we can get all over the place on the plane in terms of any amount of rotation. But the next thing we're going to look at are some very special angles to work with, things called quadrantal angles. Again, the name that they're quadrantal, not the most important thing, but what I want you to understand is when you see a quadrantal angle, think one of the ones that lands on the axis.